In this session, we shall try to find out the divergence and curl of B. We shall find out the curl of B from the case of a straight line conductor carrying a current I. A straight line conductor carrying a current is represented in the cylindrical polar coordinates as in the figure. For an infinitely long straight wire carrying a steady current I along the z direction, the macroscopic magnetic field associated is given by B at the field point S. This is equal to mu 0 I divided by 2 pi S, and this is along the direction phi hat. This is because BS is along a circular path having a radius S. Clearly, this BS has a circulation or vorticity associated with it. That means that del cross B is not equal to 0. We shall now calculate del cross B. For that, let us begin with the line integral B dot dl. We assume cylindrical polar coordinates so that a line element is dl equal to ds s hat plus s d phi hat plus dz z hat. Therefore, the line integral B dot dl, this is equal to mu 0 I over 2 pi, then close the integral 1 over s multiplied by s d phi. This is equal to mu 0 I divided by 2 pi integral 0 to 2 pi d phi, and this is equal to mu 0 I. The line integral that we have just calculated gives us a circulation of the magnetic field, and we see that the circulation depends upon the current that is flowing through the conductor. Now we shall consider this case. We have an imaginary loop as we see here, and let us assume that we have a number of conductors and each conductor is carrying different currents. So one of the conductors carries current I1, another I2, another I3, another I4, and then another I5. You can see that the conductors carrying current I1, I2, I3 and I4 passes through our imaginary loop. Now each wire that passes through the loop contributes mu 0 I, and those outside the loop contribute nothing. Now the circulation of the field or the total line integral, that would be equal to B dot dl. This is equal to mu 0 times the total current enclosed. Now if the flow of charge is represented by a volume current density J, the enclosed current would be I enclosed. This is equal to integral J dot dA. Where the integral is taken over any surface that is bounded by the loop. We shall now apply Stokes' theorem to the line integral, which is integral over a surface S, then del cross V, where V is a vector field, then dA. This is equal to the line integral over a path V dot dl, which gives us line integral B dot dl equal to surface integral del cross B dot dA, and this is equal to mu 0 times I enclosed. This is again equal to mu 0 times integral J dot dA. or this is equal to integral mu 0 j dot dA. From where we'll get the curl equation for B as del cross B equal to mu 0 j. Thus, we have found out an expression for the curl of B from the case of a straight line conductor carrying a current. The same could be obtained by using the Biot-Savart law. So in this section, we shall try to find out the divergence and curl of B from Biot-Savart law. The Biot-Savart law for the general case of a volume current is B, which is measured at the field point R with position vector R. This is equal to mu 0 over 4 pi, then integral the volume current density J is measured at the source point, which is at R dash, cross script R over script R square, then d tau prime. Let's call this as equation number 1. So this formula gives the magnetic field at a point R in terms of an integral over the current distribution J, which is defined at x prime, y prime, z prime. So the same has been shown in this figure. We have the source point fixed at x prime, y prime, z prime, and the field point is at x, y and z. The separation vector is script r. And in the integral we have considered a very small volume element d tau prime. Notice that B is a function of x, y and z, and J is a function of x prime, y prime and z prime. Therefore, we can obtain the separation vector script r as x minus x dash x hat, y minus y dash y hat, z minus z dash z hat. And the corresponding volume element would be d tau prime equal to dx dash, dy dash and then dz dash. Also note that the integration is over the primed coordinates, and the divergence and the curl of B are with respect to the unprimed coordinates. We'll now take the divergence of BR, which is del dot B, that is equal to mu 0 over 4 pi integral del dot J cross script R over R square, then d tau prime. Now we'll use the identity del dot A cross B equal to B dot del cross A minus A dot del cross B. Therefore, del dot J cross script R over R square, this is equal to R hat over script R square dot del cross J minus J dot del cross script R over R square. Now, del dot J is 0 because J does not depend on the unprimed variables. And also this term, this is also equal to 0. Therefore, we'll get del dot B as equal to 0. That means that the divergence of magnetic field is 0. We shall now try to calculate the curl of B from Biot-Savart law. We'll take the curl of B and write del cross B equal to mu 0 over 4 pi integral del cross J cross script R over R square, then d tau prime. We'll use the BAC-CAB rule and write del cross J cross script R over R square as equal to J, then del dot script r over r square minus script r over r square del dot j. But del dot script r over r square, in terms of the delta function, this can be written as del cube 4 pi into del cube script r. So this is a standard relation. We'll substitute this to get del cross b as equal to mu 0 over 4 pi integral j r prime, then 4 pi del cube r minus r prime d2 prime. This is because vector script r is equal to vector r minus vector r prime. When we integrate this, we'll get this as mu 0 times jr. Thus, the curl of B is finite, and that is equal to mu 0 times jr. The curl equation of B has a name, and this is known as Ampere's law. In differential form, Ampere's law is del cross B equal to mu 0 j. It can be converted into integral form by applying the Stokes theorem. That is, integral del cross B dot dA equal to line integral B dot dl, and this is equal to mu 0 times integral J dot dA. Now the integral J dot dA will give you the outward flux. And this is the total current I enclosed. Thus, we can write the Ampere's law in integral form as line integral B dot dl equal to mu 0 times I enclosed. Now, as an application of the Ampere's law, we shall try to solve some of the problems that we have already solved using the Biot-Savart law. In solving problems using Ampere's law, the first thing that we need to fix is the path along which the integration is to be done. This path from here onwards will be known as the Amperian loop. I shall now introduce some key guidelines or rules of thumb for selecting an Amperian loop in solving problems in magnetostatics. The first rule will be to identify the symmetry in the problem. If the current distribution has some symmetry, for example a straight wire, circular loop, solenoid, etc., we'll be choosing a loop that mirrors that symmetry. And that often leads to easy integration and quick answers. For example, in the figure shown here, we have a long wire which is carrying a current I, and the magnetic field is encircling the current carrying conductor. And we'll take that path as the Amperian loop, that is the path for integration. The second consideration is to enclose the current. That is, the loop must enclose the current that you want to calculate the magnetic field for. You can see from the above equation that the enclosed current determines the value of the line integral in Ampere's law. The third consideration is the alignment of the field. Whenever possible, we should be choosing a loop where the magnetic field is either parallel or perpendicular to the loop's path. This will simplify the dot product in Ampere's law and then make the integration easier. The fourth consideration is to have a constant magnetic field. If the magnetic field is constant along a path, then that path is a good choice for a loop segment. And this again eases integration. And finally, we should avoid unnecessary complexity. That is, we should be keeping the loop shape as simple as possible to minimize calculations. Simple shapes like circles, rectangles, or straight lines are often ideal. So, with this in mind, we shall try to solve this problem. The problem is to find the magnetic field at distance s from a long straight wire carrying a steady current I using the Ampere's law. So the problem has been illustrated in the figure. We'll be choosing the Amperean loop to contain the current, and that will actually encircle the wire as shown in the figure. The direction of B is circumferential and is circling around the wire. And by symmetry, the magnitude of B is constant around an Amperean loop of radius s centered on the wire. Now we shall apply the Ampere's law. Closed integral B dot dl equal to integral B dl cos theta, and that is equal to integral B dl cos of 0. So this is because the elementary length dl and the magnetic field are along the same direction, and therefore theta equal to 0. And this is equal to b then integral of dl, or that is equal to b times 2 pi s, that is the perimeter of the circle which constitute the Amperean loop. Now, according to the Ampere's law, we have closed integral b dot dl as equal to mu 0 times I enclosed. That means that b times 2 pi s equal to mu 0 times I, which will give us the magnetic field as mu 0 I over 2 pi s. We have proved the same result using Biot-Savart law, and we see that the use of Ampere's law further simplifies the problem. Now we shall consider this situation where we have a sheet of current on which a surface current K is flowing. We need to find out the magnetic field due to this surface current. So the problem is find the magnetic field of an infinite uniform surface current K equal to Kx hat flowing over the xy plane. If we have to solve this problem using the Ampere's law, we need to find out the direction of the magnetic field. And according to the rule of thumb, we have to align the Amperean loop according to the direction of the magnetic field. We have the Biot-Savart law Br equal to mu 0 over 4 pi integral K cross script r over script r square then dA. So the direction of magnetic field is given by K cross r. That is, B is perpendicular to the surface current K. B cannot be along the direction of x. Now we have to find out whether it would be along the y or the z directions. In order to do that, let us divide the sheet into infinite number of line elements. And we assume that all these elemental currents will add up to result in K. So if we assume the current flow along an element as shown in red color with an arrow, the magnetic field will be encircling this current element. I have fixed the x, y, z coordinates along the center, and I have identified two elemental currents on the right and left hand side of the origin. Now let us consider the elemental current on the left. The direction of the magnetic field at any point will be tangential to that particular point. And we have shown in this figure the direction of magnetic field at this particular point. Now we shall resolve that into a horizontal and a vertical component. The horizontal component is By and the vertical component is Bz. The horizontal component is towards the left and the vertical component is towards down. Now let us consider a similar point on the magnetic field that is generated by a current element on the right hand side. In this case, the horizontal component By is towards the left, whereas the vertical component Bz is towards up. So we see that when we consider 2 points on the current elements which are there on the left and right side of the origin, the vertical components get cancelled because they are in the opposite direction, whereas the horizontal components add. So in this case, when we consider points above the surface of the plane, the magnetic field is towards left. Now let us consider 2 points below the surface of the plane. If we consider this particular point, and if we resolve the magnetic field at this particular point into horizontal and vertical components, we see that Bz is directed towards up and By is directed towards the right. Now let us consider the second point on the element on the right hand side of the origin, and we can see that the horizontal component By is towards the right, whereas the vertical component is towards down. In this case also, the vertical components Bz gets cancelled and the horizontal components get added. So in conclusion, we can see that B can have only a y component, and B points to the left above the surface and to the right below the surface. With this in mind, we shall try to draw the Amperian loop. So as shown in this figure, the Amperian loop is perpendicular to the direction of elemental currents, and it has a part above the surface of the plane and the dashed part is below the surface of the plane. Now we have to indicate the direction along which we would be doing the integration. Let us take that above the surface the Amperian loop is towards the left and then it goes down, and below the surface it goes to the right side, and in the interface let us take this as going up, so that we'll get a Amperian loop. So this is the surface and this is above the surface and this is below the surface, and above the surface let us take the arrow like this towards the left, down, right, up, and this will be completing our Amperian loop. Now let us apply the Ampere's law, that is a closed integral B dot dl as equal to mu 0 times I enclosed. The enclosed current would be K times L. Now we'll write the left hand side as closed integral B dot dl. This is equal to integral minus B y hat dot minus dl y hat. This part is for the line integral above the surface, and then for the first side we shall write this as minus B z hat dot minus dl z hat. Since we are traversing down in the second path, now the third path, the line integral is B y hat, because we are moving along the plus y direction, dot dl y hat, and for the path going above we shall write integral B z hat dot dl z hat. Now I would like to introduce to you a characteristic of the Amperian loop. So let us take this width as dl dash and this as dl. In designing the Amperian loop, we'll assume that dl dash is approximately equal to 0, so that the Amperian loop is as close to the surface as possible. When we do that, we can take this term as equal to 0, that is the second term is 0, and also the fourth term is also 0. That means that the contribution from the left and right sides of the Amperian loop is negligibly small when compared to that in the top and bottom. Therefore, the line integral is closed integral b dot dl. This is equal to 2 times bl, where one bl comes from the top segment and the other from the bottom. When we equate the left hand side and the right hand side, we have 2bl equal to mu 0 times kl. Here l and l gets cancelled, resulting in b equal to mu 0 k over 2. Or more precisely, b equal to mu 0 k divided by 2 along the y hat direction for z less than 0, and this is equal to negative of mu 0 k over 2 y hat for z greater than 0. So this indicates that below the surface, magnetic field is along positive y direction, and above the surface current, the magnetic field is along the negative y direction. Now we shall try to find out the magnetic field due to a very long solenoid. We have already done this using the Biot-Savart law. We shall now explore how to do this using the Ampere's law. The question is, find the magnetic field of a very long solenoid consisting of n closely wound turns per unit length on a cylinder of radius r, each carrying a steady current I. This is pictorially represented in the figure. The cylinder is having a radius r, and the current that is flowing through the solenoid is I. We know that the magnetic field of an infinitely closely wound solenoid runs parallel to the axis. Inside the coil, the magnetic field is axial, that is along the upward direction. Outside the solenoid, it is in the downward direction. Also, when we consider a point P which is far away from the solenoid, here the magnetic field will be approximately equal to 0. With these considerations, we shall try to solve this problem. In order to solve this problem using the Ampere's law, we need to consider the Amperian loop. We will consider two Amperian loops, Amperian loop 1 which is lying outside the solenoid, and Amperian loop 2 which is lying partly inside the solenoid and partly outside the solenoid. So loop 1 lies entirely outside the solenoid with its sides at distances A and B. Loop 2 is half inside and half outside. Let us first consider loop 1. We shall first calculate line integral b dot dl. We will integrate this function along path 1, path 2, path 3 and path 4 as you see in this figure. So this is integral along path 1 b dot dl plus integral along path 2 b dot dl plus integral along path 3 then b dot dl plus integral along path 4 then b dot dl. This is equal to integral b dl cos pi by 2, because the magnetic field and a small segment of the path dl are perpendicular to each other, plus line integral over path 2, then b dl cos 0, plus line integral over path 3, then b dl cos pi by 2, plus integral over path 4, b dl cos pi. Terms 1 and 3 gets cancelled. This is equal to b at a minus b at b multiplied by L. Now b at a minus b at b multiplied by L is equal to mu 0 times I enclosed according to Ampere's law. But the current that is enclosed by the Ampere in loop 1 is 0. Therefore, this is equal to 0, and we'll get b at A equal to b at B. This equation implies that the field outside does not depend on the distance from the axis. And we also know that the magnetic field goes to 0 for large S, that is away from the solenoid. So it must be almost equal to 0 everywhere, and therefore we can write b at A equal to b at B, and that is equal to 0. Now let us consider the case of loop 2, which is partly inside the solenoid and partly outside the solenoid. Magnetic field outside the solenoid is 0. Inside, we have closed integral b dot dl. This is equal to mu 0 times I enclosed. That is b dl cos 0. This is equal to mu 0 times I enclosed. That is bl equal to mu 0 I enclosed, which is equal to mu 0 multiplied by n I multiplied by L, where n is the number of turns per unit length of the coil, from where we'll get B as equal to mu 0 times Ni. This is how we'll find the magnetic field due to a long solenoid using the Ampere's law. In conclusion, the magnetic field, this is equal to mu 0 n I along the z direction inside the solenoid, and outside the solenoid its value is 0. From solenoids, which are long coils along a straight direction, we move on to what are known as toroids. A toroid is one which is wound in a circular fashion like this. The windings inside a toroid will be uniform and close, so that each turn can be considered as a plain closed loop. So what you see here is just a loop of the toroid coil. The cross-sectional shape of the coil can be circular, rectangular, or even some weird asymmetrical shapes. For the one that we are considering here, it is rectangular. Whatever be the cross-section of the toroid coil, as long as the shape remains the same all the way around the ring, the magnetic field inside the toroid coil will be circumferential. That is, as shown by the blue lines inside this figure. In this problem, we are to find out the magnetic field that is inside and outside of a toroid coil. Before finding out the expression for the magnetic field inside and outside the toroid coil, we shall try to prove that the magnetic field is circumferential. For that, let us consider a toroid coil having arbitrary cross-section. In this case, this is the cross-section. We assume that it has no particular shape. Because of the symmetry of the problem, we may use cylindrical polar coordinate system. Let us fix the cylindrical polar coordinate system at the center of the toroid coil. Two source points are at R dash and R double dash. The field point is at R. The separation vector between the source point and the field point is script R. In cylindrical polar coordinate system, we take this distance as S dash, and then this is phi dash, and this is Z. As per the convention, in Cartesian coordinate system, this is X and this is Y and this is Z. To prove that the magnetic field is circumferential inside the toroid coil, let us consider the Biot-Savart law. We'll write an expression for the field at R due to the current at element R dash. This is given by dB equal to mu 0 over 4 pi, then I cross script R over script R square dl. This is equal to mu 0 over 4 pi vector I cross vector R over script R cube, then dl. We keep the field point R in the xz plane, and the Cartesian components of R are x, then y is 0, and then z. The source coordinates in cylindrical polar coordinates are R dash equal to x dash y dash z dash, and that is equal to s dash cos phi dash, s dash sin phi dash, and then z dash. From these, we can find out the separation vector script R as x minus s dash cos phi dash minus s dash sin phi dash, then z minus z dash. The current has no phi component in the cylindrical polar coordinate system, because you see that the current is flowing in this direction, so it doesn't have any phi component. Therefore, vector I in cylindrical polar coordinate system is is s hat, the phi component is 0, and then iz z hat. In Cartesian coordinate system, the current is is cos phi dash, then is sin phi dash, then iz. So we have found out I and script R. We shall now take I cross R. This is x hat, y hat, then z hat, is cos phi dash, is sine phi dash, then iz, then x minus s dash cos phi dash, minus s dash sine phi dash, then z minus z dash. We take the determinant. When we expand the determinant, this is is sine phi dash z minus z dash plus iz s dash sine phi dash. This will be the x component, and the y components are and then we have the z component. The y component is is cos phi dash z minus z dash minus iz x minus s dash cos phi dash, and then the z components are is cos phi dash minus s dash sine phi dash minus is sine phi dash x minus s dash cos phi dash. We shall simplify this equation, that is I cross script r. This is equal to sine phi dash is z minus z dash plus s dash iz. So this is the x component, and then iz x minus s dash cos phi dash minus is cos phi dash z minus z dash. This is a y component, and then minus is x sine phi dash. This is the z component. We'll use the bracketing now. So this is x hat, and this is y hat, and this is z hat. Now when we inspect the figure, there is a symmetrically situated current at r double dash. So this is the current flowing at r double dash, and this is the current that is flowing at r dash. For these two currents, the s dash will be the same, script r will be the same, dl dash will be the same, and is will be the same, iz will be the same, but this current element is situated at negative phi dash. Because sine phi dash changes sign, the x hat and z hat contributions from r dash and r double dash cancel, leaving only a y hat term. Thus the field at r is in the y direction, and in general the field points in the phi hat direction. We conclude that the field inside a toroid coil is circumferential and is along the phi hat direction. Now we'll determine the magnitude of the magnetic field using the Ampere's law. According to Ampere's law, we have line integral B dot dl equal to mu 0 times I enclosed. Since B is circumferential, B dot dl is B dl cos 0, and this is equal to mu 0 times I enclosed. Magnetic field is steady, therefore we have B dl, and this is equal to B times 2 pi s, and this is equal to mu 0 times the enclosed current, which is N times I, where N is the number of turns of the toroid coil. From here, we'll get the magnetic field as mu 0 Ni over 2 pi s, which is the final expression. In vector form, B, which is a function of r, is mu 0 Ni over 2 pi s along the phi hat direction for points inside the toroid coil. For points outside the toroid coil, the magnetic field will be 0.